The paper we're breaking down today is called Video Generation Models in Robotics, Applications, Research Challenges, Future Directions. It's by Zating Mei, Tenny Yin, and a whole team from Princeton, Temple University, and others. For everyone listening on the go, here's the 1-minute summary. We are seeing a huge architectural shift where video generation models, specifically diffusion and flow matching, are becoming more than just content tools. They're turning into high-fidelity, embodied world models. The big idea is that these models can simulate really fine-grained stuff, like deformable bodies, fluids, things that classical physics engines just can't handle. This opens up 4 massive areas: generating synthetic data for imitation learning and modeling dynamics and rewards for RL, visual planning, and much cheaper policy evaluation. We're basically moving from video as an output to video as a learnable physics engine. It learns the world to train robots that can do, well, just about anything.
It's a pivot that completely redefines what a simulator even is. We're not just looking at pretty pixels anymore. We're looking at a neural net that predicts the next state of reality.
Exactly. And that's the summary. So now let's get into the details, because for the ML engineers and roboticists listening, the implications here are actually pretty wild. I want to start with the why. We have large vision language models, VLMs, and vision language action models, VLAs. We've all seen the demos.
Yeah.
You tell a robot, pick up the apple, and it mostly works. Why isn't that enough?
It's what the paper calls the expressiveness bottleneck. And this is a really, really important distinction. VLMs are semantic engines. They're amazing at high-level reasoning, the what and the why, but they hit a hard wall when it comes to the how, especially on a physical, contact-rich level. The paper uses a great example. Imagine trying to describe the precise contact interactions between a robot gripper and, a crumpled piece of cloth, using only text.
Yeah, I can't even imagine. Try writing that prompt. The gripper touches the cloth at coordinate X, applying Y pressure, which then causes a secondary fold to propagate at a 45-degree angle.
Exactly. You run out of tokens, and honestly, you just run out of language. Natural language just lacks the bandwidth, the resolution to describe fine-grained physical dynamics, friction, deformation, fluid flow. It's too low-dimensional.
Okay, so if language models fail at physics, why not just stick with the classical simulators? We've had things like MuJoCo and PyBullet for years. They use actual physics equations.
They do, but they suffer from that classic spherical cow problem, right? To make the math computable in real time, classical simulators have to use all these simplifying assumptions. They're great for rigid bodies, robot arms, blocks, solid metal parts. But have you ever actually tried to simulate a t-shirt or dough in a traditional physics engine?
It's a complete computational nightmare.
It's awful. You're dealing with non-rigid deformations, really complex morphology, fluid dynamics, and even if you can simulate it, you fall into the asset curation trap. You have to sit there and manually tune friction coefficients, textures, lighting, all to match your real-world lab.
And if you get it wrong,
which you will, you end up with a massive sim-to-real gap. Your policy works perfectly in the sim, but then it fails on the real robot because the lighting is just a tiny bit different.
So the argument this paper is making is stop trying to manually code physics equations. Use video generation models as implicit simulators.
Right. A video model like Sora, or the ones they talk about here, it doesn't know Newton's laws explicitly. It's never been hard-coded with fluid dynamics equations. But what it has done is ingest millions of videos of water splashing. So it learns the phenomenology of physics. It predicts the next frame based on the statistical patterns it's seen in reality. It captures lighting, texture, deformation, all of it, just natively, because that's what's in the data.
It's data-driven physics. Okay, before we jump to the applications, I want to spend a minute on the architecture. The paper makes some specific points about the tech stack. It highlights diffusion, obviously, but it also mentions flow matching. I feel like flow matching is gaining traction, but is maybe less understood.
Oh, it's definitely the rising star for this kind of high-fidelity synthesis. Think of it this way. Diffusion is a stochastic process. You start with noise, and you take this kind of random walk, slowly denoising step by step, until you land on the data distribution. It works, but the path from noise to image is, well, it's a bit meandering.
It's inefficient.
It can be.
Yeah.
Flow matching, or more specifically conditional flow matching, tries to define a vector field that maps the noise distribution to the data distribution in the most optimal straight-line path possible. It's based on optimal transport theory. And because that path is straighter, you can often get really high-fidelity results with fewer integration steps during inference.
Which is going to be crucial when we talk about latency later.
Yeah.
But okay, whether you use diffusion or flow matching, the paper points out that doing this in pixel space is just a bad idea for robotics.
It's just too heavy. Generating 4K video, frame by frame, the compute is massive. So the standard now is latent fusion. You use a VAE, a variational autoencoder, or maybe a magbit tokenizer to compress that visual observation into a much lower dimensional latent space. You do all your generative work, all your physics prediction in that compressed space, and then you just decode it at the end.
But there's a third architecture mentioned that I think is the most exciting for our audience, video JEPAs.
Yes, joint embedding predictive architectures. This is Jan LeCun's whole area of focus. The key difference here is the goal. Diffusion and flow matching are generative models. They want to produce a video that a human can actually watch. JPAs are predictive. They don't necessarily care about reconstructing the pixels.
So they just stay in the latent space.
Exactly. They predict the future state of the features in latent space. Think about it. If I toss a set of keys to you, your brain predicts the trajectory of the object. You aren't rendering some high-res, ray-traced movie of the keys in your visual cortex.
Right, you're just tracking the concept of keys and where they're going.
Precisely. You're tracking the semantics and the location. JTAs do that. And for a robot, that's usually all you need. If you're planning a path, you don't need to know how the light reflects off a glossy table. You just need to know the table is solid and where the edge is.
Right. By stripping away that need to render pretty pixels, JPAs can be so much faster. And you could argue they learn a better representation of the underlying physics because they aren't distracted by all that high-frequency visual noise.
That's a theory.
Okay, that's the stack. Let's move to the 4 big application areas the paper lays out. Number 1 is imitation learning and data generation. We all know the bottleneck in robotics is data.
It is the bottleneck. In NLP, you can just go scrape the entire internet for text. In robotics, data has to be collected physically. You usually have a person standing there with a teleoperation rig, moving a robot arm for hours and hours just to fold laundry or open a door. It's slow, it's expensive, it doesn't scale.
So the proposal is video models as data factories.
Yes. If you have a trained video world model, you can synthesize expert demonstrations. You give it an initial image, a text instruction, and it generates a video of the robot performing the task successfully. You're basically hallucinating your training data.
But here's the insight from the paper that I found really compelling. We shouldn't just generate the perfect videos. We need to generate failure trajectories.
This is the failure feature. It's so important. If you only train a robot on successful demonstrations, the happy path, the policy you get, is incredibly brittle. The second the robot drifts even slightly off that perfect trajectory, it enters a state it has never seen before. It panics. It just freezes up.
Because it's never learned how to recover from a mistake.
Exactly. So the paper suggests using these video models to intentionally synthesize failures. Dropping the cup, missing the grass, bumping into the table, and then, crucially, synthesizing the recovery from that failure.
That is such a clever use of generative AI.
Yeah.
You're using the model to expose the robot to all these edge cases that would be dangerous or just a pain to set up in the real world.
It's all about building robustness. But there is a little technical catch here. You have a video of a robot moving that's just pixels. A robot needs motor torques or joint velocities. You can't just feed an MP4 file into a PID controller.
Right. You still need the actions.
So you need what's called an inverse dynamics model. It's a separate system that looks at the transition between frame T and frame T plus 1, and it infers, okay, what action must have been taken to cause this visual change? It maps the visual hallucination back to actual executable motor commands.
Okay, let's move to the second application. Reinforcement learning and world models.
Right. In RL, the agent is basically running this continuous loop. If I do X, what happens to the world, and is that good for me? Traditionally, you need a simulator to answer those questions. This paper argues the video model is the dynamics model.
But they make a distinction between implicit and explicit video world models. This seems like a pretty crucial architectural choice.
It is. A so-called implicit model means the world exists only within the video generation process itself. You give it a state and an action, and it just outputs the next frames. Systems like Pandora or Vid2 World work this way. They're end-to-end pixel predictors.
They're explicit.
Explicit models use the video generator to actually construct a consistent 3D or even 4D representation of the scene. The paper mentions a system called Enerverse, which uses multi-view video to train 4D Gaussian splatting. Or another one, Aether, which generates depth maps and camera remaps.
So Aether isn't just dreaming up images, it's actively trying to build a 3D geometry of the scene from the video.
Yes, it's the difference between painting a picture of a room and building a 3D CAD model of it. And explicit models are generally better for physics consistency because they enforce that 3D geometry. You handle occlusion better. If a robot arm goes behind an object, the object is still there in the 3D space. In a purely implicit pixel model, that object might just vanish from existence.
And we have to mention Genie Envisioner here, which feels like the closest thing we have to a foundation model for robot action.
Genie Envisioner is really impressive because it's completely end-to-end. It trains the video generator right alongside an action decoder. It creates this latent action space, so it can go directly from latent video states to predicted discrete actions. It closes the loop between seeing the future and acting to create it all inside a single architecture.
That leads perfectly into the third application, policy evaluation.
Yeah.
This is all about solving the trust problem.
Yeah, and this addresses a huge logistical pain point. Let's say you've trained a new policy. Is it actually better than the old one? To find out, you typically have to deploy it on a real robot and run, 50 or 100 trials?
Which takes all day, requires a human to reset the scene every single time, and you risk smashing your expensive hardware if the policy is just bad.
Exactly. So instead, you use the video model as a virtual sandbox. You let the robot roll out the policy visually. The robot imagines acting, and the video model predicts the result. If the generated video shows the robot dropping the object, you mark it as a failure.
But how do we know the video judge is being fair? I mean, if the video model hallucinates that I succeeded when I actually would have failed, the whole evaluation is worthless.
That is the core validation question, you're right. The paper discusses two key metrics for this. First is the Pearson correlation coefficient. They measure if the success rates they see in the video simulator track linearly with the success rates in the real world.
So if policy A is, say, 80% successful in the video and policy B is 40% successful, we'd want to see that same kind of spread in reality.
Right. Even if the absolute numbers are a bit off, maybe the sim is harder than reality, as long as the correlation is high, it's still useful. The second metric is MMRV, or mean maximum rank violation. This specifically checks if the video model ranks the policies in the correct order.
It's like grading on a curve. As long as the A student still gets a higher score than the C student, the ranking holds up, and we know which policy we should deploy.
Exactly. It allows researchers to do this off-policy evaluation on thousands of checkpoints without ever touching a physical robot. That just massively accelerates the iteration cycle.
Application number 4 is visual planning. This feels the most sci-fi, but it's also the most logical extension of all this tech.
It's essentially model predictive control, or MPC, but happening inside the imagination. Instead of just reacting, the robot uses the video model to simulate multiple future trajectories. It asks itself, what if I move left? What happens? What if I move right? It generates these little visual dreams of the future.
And then it optimizes based on what it sees in those dreams.
Right. It runs an optimization algorithm like CEM, the cross-entropy method over these imagined futures, to find the one trajectory that maximizes the probability of reaching the goal. It finds the best path before it even moves a single muscle.
It's literally look before you leap. But the looking happens inside a generated video.
Or in a latent space, if we go back to that JEPA approach we were talking about.
Okay, we've painted a pretty rosy picture here. Video models are physics engines, data factories, virtual sandboxes. But the paper dedicates a big section to the reality check. What breaks?
A lot. The biggest hurdle, by far, is hallucinations. We see this with text LLMs, but in video, it's arguably so much worse. Objects might just flicker in and out of existence. That's the object permanence issue.
Or the physics just completely breaks down.
Right. The paper calls it violations of physics. If the video model thinks a ceramic mug is deformable, it might show the robot squeezing the mug like it's a sponge. If the robot then plans based on that, it's going to crush the real mug. The model is just minimizing pixel error, not enforcing conservation of mass.
And this comes back to the fact that these are probabilistic models, not causal engines. They're just guessing what looks right.
Exactly. Then there's the drift problem in long horizon tasks.
This is the folding laundry example again, isn't it?
It is. You tell the model, fold the laundry, the first 10 frames look great, but by frame 100, the shirt has morphed into a towel, or the background has changed completely, or the robot arm has suddenly switched colors. Maintaining that semantic consistency over a long time horizon is incredibly difficult for these autoregressive models.
And then there is safety.
This is critical. If we're using these models to generate training data, and the model hallucinates a trajectory where the robot moves unpredictably or dangerously, like swinging a tool wildly, and we train on that, that's not just unsafe content in the normal sense. That is physically dangerous kinetics. We need safety-aware generation.
And finally, the boring but very real constraint, latency.
Inference speed. If it takes you 10 seconds to generate the next frame of your plan, you can't use it for real-time control. A robot needs to react in milliseconds. That's why those latent space approaches, the JEPAs we talked about, are so vital. They are probably the only path to getting the necessary hertz for closed-loop control.
So wrapping up the paper's outlook, where is this whole field going?
The field is clearly pushing for a longer, more consistent video generation to solve that drift problem. We're seeing better instruction following, but the macro trend, I think, is the convergence into what they call unified world models.
Meaning one giant neural network that does it all.
Yes. Instead of having a separate vision encoder, a separate dynamics model, and a separate policy network, we're seeing these end-to-end architectures where one model handles the dynamics, the rendering, and the semantic understanding all in one.
It really feels like we're on the cusp of the GPT moment for robotics, but it's being driven by video, not text.
I think that's a fair assessment. I mean, when you can simulate the world faster than real time with high fidelity, you basically solve the data problem. And once you solve the data problem in robotics, the capabilities are just going to explode.
I want to leave our listeners with a thought that really struck me while reading about the video GMA. That idea of predicting features instead of pixels.
It's a profound shift in perspective.
We tend to judge these AI models by looking at the video output and saying, oh, that looks realistic to my human eyes. But if a robot can dream up a solution in some high-dimensional latent space, a mathematical abstraction, without ever rendering a single pixel for us to see.
You have to wonder, are we actually limiting the AI by forcing it to produce video that we can understand?
Exactly. Maybe the most accurate simulation of the universe isn't a movie we can watch, but a matrix of vectors we can't even begin to comprehend.
Yeah.
Have we created a machine that understands the physics of the world better than we could even visualize it?
It's very possible. At the end of the day, we should be optimizing for robot performance, not for human entertainment.
Something to think about next time you see a cool robot video.
Yeah.
This has been the AI Paper Podcast, breaking down video generation models in robotics. Thanks for listening.